All right, so yeah, thanks for having me. Today I'm going to talk a little bit about using a reservoir computer for the task of reconstructing coupled chaotic systems, and in particular we want to look at coupled chaotic systems that are going to be displaying generalized synchronization, and also what role does the memory of a reservoir computer play in this task. So this is work that I've done together with Dave Walker, Michael Small, and Thomas Jungling, who's up next, talking next. So I guess we're going to start off with a little brief outline on what reservoir computing is, what the general idea is. So when you drive a dynamical system with some input, so when you drive a dynamical system with some input, the response of that system to the drive signal is naturally going to perform a computation of the input signal. And the philosophy behind reservoir computing is to utilize those natural computations performed by your systems to perform some sort of specific task. So what you do is you have your interesting signal that you want to perform a computation on. You somehow, so that's here, you somehow inject it into your reservoir, which is some sort of large dynamical system. There's some more properties it needs to have. But when we say large, what we really mean is we want it to have some sort of diverse set of responses to the input signal. You then measure all those responses, and you want to utilize them to synthesize some sort of target signal. So that's the general idea behind reservoir computing. And one of the key properties of reservoir computing is that it has memory, right? So it's a real key property. This enables it to do all sorts of sequential processing tasks and tasks of a temporal nature. We saw some just in the talk before, but you can do things like time series prediction, speech recognition, robotic control, all kinds of things. You can also use all different kinds of systems as your reservoir. So there's a lot of work done with using neural networks, and that's where the ideas originated from. But there's also a lot of very interesting analog types of reservoirs, so physical substrates, optical circuits, robotic limbs even. So these sort of physical versions of reservoir are very interesting and got a lot of potential. The one we will use today, though, is the echo state network, which is one of the original neural network forms of reservoir computing. Essentially, for an echo state network, all you've got is that you're putting a recurrent neural network as your reservoir, as your dynamical system. So your recurrent neural network is determined by your internal connection matrix W, which determines how the nodes of your network are connected to each other, and this input vector V, which determines how you're inputting your input signal into all of the nodes. You keep these fixed, right? And then you run your system according to this equation. Beta is just moves you around on your 10H activation functions. You then measure all your response states, and you want to then use this train with the linear regression, your readout vector, which is going to synthesize your target function. And again, the key property here, one of the key properties is fading memory, right, which is closely related to the echo state properties for echo state networks, where you have the state of each node is a function of the history of the input. This is a really key property that allows it to do processing on temporal tasks. And there are many parameters, many parameters in the network, but you typically reduce down to a few sort of hyperparameters and network structures that you're looking at, but there's lots of different ways to set up these types of networks. I'm also going to have a quick little introduction to what generalized synchronization is. That's what we're looking at. But essentially, it's a form of synchronization that's common between coupled chaotic systems, but generally different chaotic systems, typically different, but it can be the same chaotic systems. It can be unidirectional, but today we're just going to focus, it can be bidirectional, sorry, but we're just going to focus on a unidirectional case where we have, for example, the autonomous system X, which runs autonomously, but we also have this the system Y, which is driven by the autonomous system X. And we would say that these two systems are in a state of GS if the response system Y is a function of, or is a functional relationship between the response system Y and the drive system X. But the thing about GS is that this function can take many different forms. It can be very, very complicated. So methods such as correlation or mutual information may not be the best way to figure out if you do have GS or not. One way to do this, there are many ways to look to see if you have GS or not, but what we'll do today are the conditional Lyapunov exponents, which, as the name suggests, are the Lyapunov exponents of your response system conditioned on drive. So you can work them out by this sort of equation for the perturbation, the growth of the perturbation, but you're going to condition them on the drive by setting the perturbation in the drive system to 0. And so if your conditional Lyapunov exponents, if all of your conditional Lyapunov exponents of your response system are negative, then you're conditionally stable with respect to the drive and you're in a state of GS. But they also tell you about a particular form of GS that we're interested in today, which is weak GS, as opposed to strong GS. So weak GS occurs when the largest conditional Lyapunov exponent is larger than the smallest Lyapunov exponent of the drive system. So what this essentially means is that the dynamics of your response system aren't yet being completely dominated or suppressed by the dynamics of the drive system. And if we think about the Lyapunov dimension of our combined attractor, right, we can see that if this is the case, then some of the Lyapunov exponents of our response system are going to come into the calculation of the dimension. And so the dimension is actually going to be larger than the dimension of the drive system alone, as opposed to the case with strong GS, where the largest Lyapunov exponents all come from the drive system. And so the dimension of your combined system is just equal to the dimension of the drive system. In the case of weak GS, the dimension of your combined system is going to be larger than the dimension of your drive system, even though we have this sort of functional relationship between the response system and the drive system. And so where this extra dimension comes is in this function itself. So this function can be fractal in nature. So potentially a very complicated function. We're going to delve a little bit more into this, into looking at two different ways to look at these functions in weak GS, and hopefully one of them is more useful than the other. So to get started, we'll consider a simple system which displays GS so that we can avoid working in this sort of work with proper coupled chaotic systems, because then things become very difficult. But we'll start off with this low pass filter where we have an invertible chaotic map driving a low pass filter. So kappa here is a filter constant, which somehow determines the time scale of the filter. Pardon me. G is a function, is an observation function, so it's you're observing your chaotic map. And so if we unfold this second equation here, unfold it in time, we can get this relationship here where we're saying that the state of our filter is a function of the history of the chaotic map. Right? But given that our map is invertible, we could also have an alternative representation where we take the history of the map, and through iterating the inverse map, we write this the GS relationship as a function of the instantaneous state, right? So we've got these two equivalent representations here, but they offer us something different, right? So in this representation here, which we'll call the temporal representation, right? The function is actually quite simple, right? So we just have a linear combination of these observation functions, which are typically going to be relatively simple functions. But we need to have access to the memory, right? We need to know what all of the history of the chaotic map is in order to use this function, right? But on the other hand, in this second version of the function over here, which we'll call the instantaneous case, you don't need to know that that history of your chaotic map. But the function itself is much more complicated because it's got all these iterates of the inverse function here. So if we think about this from a modeling perspective, you can imagine that some sort of modeling technique which has access to this history here could utilize this simpler temporal representation of the GS function rather than this more complicated one here, right? So let's get into modeling this thing. Essentially, we're going to be using a reservoir computer to do it. But let's first, actually, we should introduce the system that we're going to be looking at. So we're going to be looking at a coupled, unidirectionally coupled Rössler-Lorenz system that displays generalized synchronization. So we've got a Rössler system, a Lorenz system. These terms here represent the coupling. K is a coupling strength. And we also have this factor theta in here, which adjusts the timescales of the two systems so that they're roughly similar. So here are a few examples of slices through this system, showing what sort of different relationships can be possible. So at k equals 0.1, we don't have any synchronization, and we see that there's really no pattern going there at all. But at k equals 1, this is an example of synchronization. This is weak GS. And we see it's actually quite a complicated relationship. It's not very obvious necessarily that there is a functional dependence there. K equals 10, we also have weak GS, but we're a much more simple function here. And k equals 50, this is where we're really starting to turn the coupling strength up quite strong, and the coupling terms start to dominate, and we're getting closer and closer to essentially complete synchronization. All right, so let's throw a reservoir computer at this. So we're going to throw a reservoir computer at it to try and model this function. So over here we can see the different regimes. So if we look at the bottom panel, we can see the conditional Lyapunov exponents, as well as the Lyapunov exponents of the drive system, as well as the dimension. So if we look in this pink regime here, we see that there is a positive conditional Lyapunov exponent, and so we don't have GS. In this blue regime in the middle, I don't know how clear that's coming up. It's probably quite difficult to see, but essentially from about 0.2 all up to maybe about 20 or so cases, 20 or so, we have weak GS, right? Where the largest of our conditional Lyapunov exponents is still larger than the smallest of the Lyapunov exponents of the drive system, right? And then over here we've got strong GS, where you have that the instantaneous, simple instantaneous function over here. And so what we see over here, we can see the performance of the reservoir is that in this intermediate weak GS regime, the reservoir can reconstruct what should be a very complicated function. Right? So this does seem to suggest that the reservoir's memory is allowing it to access the simpler temporal representation of the GS function. We can also see that there actually isn't a huge difference between what's going on towards this sort of simpler area in the weak GS regime and the strong GS regime. So even though you expect the strong GS functional to be quite a lot simpler, there is actually a huge change in performance going from there to there. So we think that it is the reservoir's access to this fading memory which is allowing it to do this. To test this hypothesis, right, we are going to essentially remove memory from the reservoir. That's quite easy to do. All you have to do is set your internal connections to 0, so remove all internal connections. Now you have signal coming into the reservoir, gets transformed by the nonlinearity, and then it's immediately forgotten, right? So there's no more signal bouncing around inside the reservoir. What we do have to be careful though is that the memory allowed us to perform a delay embedding. So to account for the fact we no longer have this delay embedding, this time delay embedding, we're going to make sure that we have 3 input channels for each of the variables of the Rössler system. So this is what the structure now looks like. Essentially, we have now a random feed-forward neural network, right? with no training of the internal weights. It should, just with the readouts. And this is, again, the results of the training on those same regimes, right? So we see here the full reservoir compared to the memoryless reservoir. We see a much sharper improvement in performance for the full reservoir in this weak GS regime as compared to the memoryless reservoir, which doesn't really see a rapid improvement in performance as coupling strength is increased. However, this is actually flipped around in the strong GS regime, where the memoryless reservoir significantly outperforms the standard reservoir. So what we think is happening there is that the full reservoir has its capacity spread over functions of different time spans, right? So it's got some functionality of the previous time step and 5 time steps ago, and etc. Whereas the memoryless reservoir only has functionality of the instantaneous input signal. Now, given that these strong GS functions over here are functions of the instantaneous functions rather than these temporal convolutions that we have in the weak GS regime, the effective size of the memoryless reservoir in this strong GS regime is essentially much larger than the full reservoir. So that's why we think we're seeing this discrepancy over here. So it does seem to be that in this weak GS regime, the full reservoir is able to utilize its fading memory to access that simpler temporal representation. But we're only comparing either full memory or no memory at all. So we want to be able to look at some sort of intermediate and control the amount of memory that our reservoir has and see how does that affect things, right? So there are many different ways to control the memory of the reservoir. You can change the spectral radius, as the previous speaker said, or you can change the size of your reservoir. You can change the size of your input vector. But all of these things are going to change other properties of your reservoir. So we want to use a technique that is going to essentially leave the reservoir alone, but reduce the memory somehow, right? And so what we're going to do is utilize a technique which is based off the backpropagation through time method, and there's an unfolding of a recurrent neural network in the backpropagation through time method, where you take your recurrent neural network. So we have this recurrent loop here, where we have connections with a time step between the network and itself. We're going to unfold these over time into a layered structure like this, right? So if you unfold this over an infinite number of time steps, this is equivalent to your original recurrent neural network. But if you truncate your unfolding of this network at some lag d, right, you're essentially only allowing signal to propagate through your network for a certain number of time steps, right? And so if you were to truncate it within the typical memory of your reservoir, then you're essentially going to be able to reduce the memory, because you can only have information about the time steps. So what this does to the memory profile, so this is an example of a memory profile over here of a typical reservoir in the black, and the dashed lines show the memory profile of a reservoir that has been truncated according to this method. So essentially, it basically follows the same profile, but we have a sharp drop when we've at the point where we've truncated it. Right. So we're going to control the memory of these reservoirs and again apply it to the same task. But before we get into the results, so a little talk about sort of what we expect to happen. Right. So if we recall, this here is the temporal representation of our toy system from before. Right. We can think about what if we had a modeling technique and we were trying to model this relationship, what would that look like? This function g here is, you can think of it as actually a relatively simple function that in the case of the Rössler-Lorenz system, you can't imagine it being more than a second order function, right? It should be something that a typical reservoir would be able to account for, right? So we can think about our modeling technique as being able to accurately model G, but only up to a certain memory depth. We only have memory up to a certain point. So we have this truncated sum where we're summing up to memory depth D. And then if we think about then, well, what does my error look like if this is my model of the GS function? Well, it comes from the remainder of the sum after this truncation. And we can actually show that the normalized root mean squared error is proportional to kappa to the power of D. So we expect an exponential decrease in the error as we add more memory according to D, right? And so on the right here, this is the performance of a reservoir truncated at different memory depths, so for a different number of layers, and we're looking at different values of the coupling strength, which sort of correspond to different time scales of the GS relationship. And so we're looking for a scaling region, and we're finding that those here. These are given in the red, right? And from these we can extract the gradient, and we get sort of the decay rate of the error with increasing memory. So if we extract this from a bunch of GS functions of different coupling strengths, which correspond to different time scales, we want to then plot these not these decay rates, but we're going to plot the inverse of the decay rates, the decay time, against the Lyapunov time of the GS function, which depends on the coupling strength. So for stronger coupling, we have a shorter time scale. For weaker coupling, we have a longer time scale. So we can sort of think about this as, the time scale of our GS function, and this error decay time over here, we can actually think about this as, considering that we're having the time in the error decay time is memory, we can think of this as saying, well, how much memory do I need to add to my system, right? Add to my reservoir in order to decrease my error by a factor of E. That's essentially what this is telling us. So we can see that we've got sort of three distinct regions here for the low timescale GS functionals. We have this deviation, and we have another deviation up here for large timescale. But in the middle here, in this sort of middle region here, we get actually very good agreement, which suggests that it is the timescale of these GS functions, which tells us how much memory we need to reduce our error. How am I doing for time?
You have about 3 minutes left, including questions.
Well, I might end it there then, right? So, thank you very much.
Okay. No, very nice talk. Yeah, sorry, I should have given you a time warning earlier. Do we have any questions in the Q&A or the chat? I can start with a hopefully quick, naive one, very naive question. So both you and the previous talk kind of have these reservoir network setups, but you chose a discrete formulation with the time step d delta t. Does that matter too much, or how important is that?
So it can matter. So so I sort of brushed over it, but we're working with, obviously, with flows here, right? But so you want to make sure that the sort of your input somehow matches the dynamics of your reservoir. So we're doing this sampling here to make our input more discrete-like. So you would want to match that up, but they both work. Yeah, I've generally worked with the discrete time ones. I don't have too much experience with the continuous versions.
Okay, no, thank you very much. Were there any other questions? We have time for one more. If not, I guess thank you. Oh, yes, we do have one. Right, so can you see that in the Q&A? Sure,
yeah. So that's the normalized root mean squared error. So you have the output of your reservoir, and you have your target signal. So you calculate the error, so normalized root mean squared, use the error, you square it, take the mean, the mean over time, square it, and then you normalize that. The normalization is the standard deviation of the target signal, if I recall correctly.
Okay, and I think that does well on time. So thank you very much again for a very nice talk.